Well, hello and welcome YouTube. Mr. Robinson back here with another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Hey, step on inside. We are going to finish our series on rational expressions, equations, and functions, whether we are multiplying, dividing, adding, subtracting, solving, or graphing them. I already did a mixed review on some other problems in the past, but no, I actually take it back. I did not. That was a paper version. So you're getting a good video version of everything as one together here. 12 problems to do. I believe it's 2 multiplying, 2 dividing, a combination of 4 in the adding, subtracting department. I think more in the adding, more in the subtracting than the adding, 2 solving, and 2 graphing. And not necessarily in that order, but I'll jump into these. And if you want to see some more, let's get those as a timestamp in the description section down below when I'm able to get those in there. Without further ado, guys, let's go ahead and get started. This is a practice exam for my students as well, something that they can get clarification of, make some sense of, and really hone in on. Now, it's assuming that you know a little bit about factoring. It's assuming you understand about dividing by 0 and restrictions, like that we've seen these things before. I don't want this to go way so long that, you know, it's beyond reproach here. I want to make sure that it's more so it's a solution guide video is what I'm doing here, but it gets a nice mixed review of some things. Not the hardest of the problems. There are some problems that ask you to be a little creative as far as what you're doing. It really has to do with understanding negatives. Factoring out negatives where negatives exist in a fraction, things like that. Without further ado, guys, let's go ahead and get started. We have 2 multiplication problems, numbers 1 and 2, where we simplify each of the expressions and state any restrictions. To simplify an expression will mean a couple things, including having this all written as a single fraction. Now, when it's written as a product of these 2 separate fractions here, that does not mean that we are not dividing things like 5x minus 60 isn't also dividing by 5x plus 60. Not that you can cancel anything out there, but just make sure that you understand that things that are on top on the left can divide on things on the bottom right, and things on the top right can divide by things on the bottom left. I don't have to write them all as one fraction for that to apply, as long as it's multiplication right here. So what I am going to do, though, also what this means is divide things that are on top and bottom that would cancel, that are identical quantities, factors that are there. So let's start by factoring anything here that we can. 5x minus 60 has a common factor of 5. If I factor the 5 out, inside of there would be x minus 12. Now down here there is an x minus 12 as well, which I will of course happily be able to cancel out a quantity right here and right here as they're factorable. I'll do it in a moment. Let's just kind of get everything spelled out. I'm in no rush to do anything there. I want to cancel everything on the same step, on the same level, and not overdo some versus others and stuff like that. I don't want to miss out on something I shouldn't have. Now, multiplying right here, 4 is a common factor of the greatest common factor of those, and you're left with x plus 12. And then this is divided by the 5x plus 60 also has a common factor of 5, and there you have x plus 12. So at this stage, I think it's worth stating that everything here is factored. We have a product of these things, and now we're looking at saying what can divide on top and bottom. And anytime I say the word cancel when it comes to dividing on top and bottom, I want to make sure that, maybe I won't always air quote, but I want to make sure that you understand canceling doesn't mean it makes it go away. Canceling means dividing something by itself, which means it becomes 1 under the assumption that we are dividing non-zero values, and I'll get to that when we talk about restrictions. So I have an x minus 12 over x minus 12 here, and that becomes 1, or it cancels, and x plus 12 over x plus 12 right here as common factors that cancel. And 5 over 5, of course, is 1 as far as cancellation goes, and we're really just left with 4 divided by 1, and 4 divided by 1, of course, is 4. Who knew that this whole thing right here is just the value 4? Assuming that x couldn't be certain values here. And the values that we're talking about, of course, without over-teaching it, is that as we especially look in factored form, we say that at any time, guys, we cannot have allowed to substitute an x value that would let us divide by 0. Prior to cancellation, and remember, cancellation doesn't mean it's gone. It means we're dividing some non-zero number by itself. If we did plug in 12 for x right here, you'd be doing 12 minus 12, which is 0. Big no-no. You can't be dividing by 0, even if it's 0 divided by 0. Plugging in 12 for x would have been a big issue here. X cannot equal 12. Doesn't matter, again, if it divided or not. Same thing with this value right here. If I plugged in a negative 12. And you know what it is as far as a factor. It's the opposite of the value that you see here. Negative 12 plus 12 would have given me 0 as well, and that's an issue. X can't equal 12, X can't equal negative 12. X can't equal positive or negative 12. Those are my restrictions for number 1. And yeah, those would have been the only issues there. All right, so again, I'm probably overstated on that first one, but that's really what we're looking for. Values that would make us divide by 0. And in a case of when we graph these, anything that canceled that would have been divided by 0 would be considered wholes. Not asymptotes, but wholes. All right, let's do number 2. Number 2. 3x minus 9 over x plus 12. Let's go ahead and find a greatest common factor here of 3 on top, and we're left with x minus 3. Divided by that x plus 12. Looks like nothing can immediately cancel, and I'm totally fine with that. And then multiplying here, I need to get into factorization of this. I'm going to dive into that momentarily. Give me one moment here. While I factor also down here on bottom, just because I want to do this all at one step, 6x squared minus 3x minus 45 has a common factor of 3 that I'd love to pull out there and get a 2x squared minus x minus 15. So I'm going to attempt to also factor down here the 2x squared minus x minus 15, while a 3 happily stands on the outside of that. So, okay, I got to factor out this top part, 2x squared plus 7x plus 5. If you factored with me before, you know we like to go into the mental factor zone here, where I'd love to try and get a 2x times x going to get me 2x squared. This is assuming it's factorable, and I've already done the problem. It is. But, you know, assuming it's factorable, this is what we're trying to spell out. Positive product, positive sum gives me a plus and plus. 5 is 5 times 1 or 1 times 5. So either I place a 1 and 5 here, and I get 10 plus 1, which is 11. That doesn't work. Or I do 5 and 1 here, which is 2 plus 5, which is 7. Again, if you know what I'm doing with that factoring stuff, then I think that's going to be helpful. All right, so there's the factorization of that there. Now I'm going to work on this 2x squared minus x minus 15. So again, a 2x squared lets me know that this is some form of 2x times x, assuming it's factorable. Now, strategies that can come into play here, besides the whole potential plus and minus, because a positive times a negative should give me a negative product here. And who knows where it actually goes. But one thing I got to consider is that, you know, as I'm looking to find things to cancel here, I really want to make almost heavy assumptions that it's possible that they were setting something up for setting something up for us to cancel. Which means maybe we're going to be canceling a 2x plus 5 with 2x plus 5, maybe an x plus 1 with an x plus 1, or maybe an x minus 3 with an x minus 3. And I'm willing to look at the potentiality of the 2x plus 5s here to start with, just because. So if this is 2x plus 5, and here's the thing, 5 is a factor of 15, so it's very possible that it's 2x plus 5 here, because if this was a positive 5, that would make this a negative 3. 5 times negative 3 is negative 15. I hope this is the case, because that would cancel x minus 3s, it would cancel x plus 5s, 2x plus 5s, that would be a good day in the office. Is this it? Negative 6 plus 5 is negative 1. Yes, it is. That is it. And, you know, that's something I'd be looking to hope to try first or among them anyway. But again, as we're looking to cancel things, using that little leverage and factorization is something that you don't want to frown upon doing. You don't apologize for having them grace you and gift you with the possibility of making something faster. I made it a lot slower in explaining it, but if we find another thing like that again, I'm going to make sure to talk about it again. There aren't a lot of problems that we're doing things with a higher, 2 isn't a higher one, but it's more than 1. Anyway, 2x plus 5 over 2x plus 5 cancel. X minus 3 over x minus 3 cancel. And 3 over 3 cancel. You are left with x plus 1 over x plus 12. And that's the extent to which we can simplify this thing right here, provided that we list some restrictions on this thing. So x plus 1 over x plus 12 is the final simplified result, meaning this is equivalent to this, provided that x is never allowed to be negative 12, as this would divide by 0 here. Or 3, look at that 3 right there, that would be a trouble spot. Or, you know, 2x plus 5 also couldn't equal 0 at any time either. What's the problem with 2x plus 5 not equaling 0? Well, that means that x couldn't equal, let's see, subtract 5 from both sides and divide both sides by 2. X couldn't equal negative 5 halves. So you're going to see me do stuff like that a little more so in a mental way. I'm going to say subtract 5 divided by 2. And you can possibly recognize where I'm getting that restriction there. So those are the three restrictions. You might suggest, hey, what about x not equaling -1? We can divide from 0. We can do 0 divided by a non-zero value. We just can't divide by 0, and we can't do it at any time. Hang on, I hear an alarm going off. Okay, I'm back, and I have no idea what that alarm was for. All right, so I think I saw a restriction here. So I can have -1. If I plug in -1, I get 0 divided by 11, which is 0. We can get 0. We just can't divide by 0. We can't get 0 over 0 as well. Anytime you divide by 0 is an issue. That's why 3 is an issue. That's why -5/2 is an issue. All right, let's go ahead and move forward here. And we're going to hit numbers 3 and 4, which involve division. Very similar to multiplication. Just two things to be aware of when it comes to it are, number 1, we will end up dividing by the reciprocal of the divisor right here of this fraction. So we'll flip that eventually as we multiply by it. And number 2, when it comes to restrictions, make sure again that at any time you're ever dividing by 0 that you mention it as a restriction. All right, so number 3 here, 8. I'm just going to keep that as an 8, of course. And this divides by factoring out a 6. We get x minus 4 from that bottom part. And I'm going to leave it as divided by for one brief moment. I want to re-remind you of the fact that although we're going to flip this thing, I want to get you a factored form of what's going to be on bottom here when I do any factorization, so we can talk about the idea that nothing there can have ever been 0 before I flip. So 3x plus 7 needs to stay exactly as such. I can't factor anything out. Down here I can factor out 6, and you're left with 3x plus 7. Although you're noticing some things that can potentially, cancel, like the 3x plus 7s, let's just keep it there for a moment as I will cancel all at one time. So this is where we are going to be able to do a flippity-floppity-flew. 3x plus 7 goes on bottom, 6 times 3x plus 7 goes up on top, and we get 8 over 6 times x minus 4 times 6 times 3x plus 7 divided by 3x plus 7. And at this time, we are looking to find things to cancel, simplify, go in that realm. Keep in mind, 8 is not dividing by like this stuff here, right? So 8 doesn't divide by this 6, for example. When you flip it, now you see what 8 actually divides by. This and, of course, that. So just, be careful. Don't cancel anything, especially across early on. That's exactly why I'm not doing things early. All right, the 3x plus 7s do go away, though, regardless of whether you flip them, what have you. And I do have 6 now dividing by 6, if you notice that. We have 8 over x minus 4 remaining, and that is all that remains. That is the simplified version of this. 8 over x minus 4, bada boom, bada beam. And there you have it. Now, as far as restrictions go, of course, what is x not allowed to be here? Well, 4. And then, you look at that 3x plus 7, regardless of whether it was on bottom before or is on bottom now, having been canceled, x couldn't have equaled, 3x plus 7 couldn't have equaled 0. So if you subtract 7 and divide by 3, x couldn't have equaled -7/3 as well. That would have been another restriction on this thing. But this is the simplified version, the equivalent to that. All right, number 4. Let's play the factor game as we look to factoring on top with that quadratic trinomial. In a 1x squared scenario, we're trying to find two numbers that multiply to make 24 and add to make -14. And that is going to be the values -12 and -2. Divided by. Now, I have a 2 minus x, and this is something of a commonality that you actually are going to notice on a couple of problems here. Let me get to the highlight and gist of it, because you might have only heard about this once in a single video that I had. 2 minus x is not in standard form. We see everything else here has been in standard form, leading terms with x and even the x squared before anything else like that. This is the only thing we've seen that is not in standard form, and it just so happens to look really close to x minus 2. Now, 2 minus x and x minus 2 are not the same thing. I'm convinced that a lot of people are convinced that they are. But I promise you they are not the same thing. But they are very, very close and very similar in such a way that, man, if only they changed spots. But not just changing spots. If you really think about it, guys, it's really all about 2 minus x is the same thing as -x plus 2. If I reorder the terms, the x is staying negative and the 2 is staying positive. There's no changing that. Unless you work for what we call a greatest common factor. Why do I factor a 6 out of the 18 and 42? Because 6 is the greatest common factor. You know what? This has a greatest common factor as well. It's not just a 1. It might not be a number that's more than 1. It's actually a negative 1. Whenever you have a leading term that's negative, and by leading term, I'm mentioning kind of that this is in standard form, the x term being first. When the leading term is negative, I can factor a negative 1 out of there, or a negative, and I'm left with x minus 2 on the inside. Once again, I reordered these so that this was in standard form. The x term was first. And in standard form, I now have a leading negative. If I factor that negative out of there, look in distribution form. The opposite of x is negative x. The opposite of negative 2 is positive 2. And we have the equivalent of this expression now. But in such a way that, I mean, why did I do this? I guess because there's recognition that I had an x minus 2 here. Yeah, I can cancel these things now. Would have that been important before? Actually, yeah. You know, you want to look for things that you can factor, any common factors whatsoever. And I've never, ever, I've never ever shied away from the fact that you should be factoring all greatest common factors. I'm afraid, and I'm worried, that you just heard me say you should factor a lot of greatest common factors. No, what I actually said is you should factor all greatest common factors, including negatives. All right, spending a lot of time on this one. I feel like you're owed a little bit more explanation for that one, because this is not the last time this is going to show up in this video. All right, so I did factor this. Believe it or not, I factored. And yes, we'll do some cancellation, but let's keep going. Divided by, on top here, we have a 1x squared, and again, I'm trying to find two numbers that multiply to make negative 36 and add to make negative 9. That looks like a negative 12 and positive 3. So I'm going to get x minus 12 times x, what did I say, positive 3, plus 3. And down here, I have once again a common factor of not just a 2, but also an x here. And I'm going to be left with x plus 3 down there. Great, so I have everything factored as best as possible. And of course, I'm going to look for cancellation items. But before I go ahead and flip this thing over, let's look at that in its factored form there. And now let's do multiply and divide by, multiply by the reciprocal of the divisor. Now, this negative, guys, I'm going to have you know that this negative really can float anywhere under the sun. Remember, it is a negative 1. When you divide by a negative 1, that's the same thing as dividing from a negative 1. There are things where people have trouble with the existence of a negative, especially in a fraction. And, you know, just me factoring out the negative to begin with. Fact of the matter is, guys, whether I have the negative right here or the negative right here, it's not going to matter. And I'm not asking you to put the negative up there. I'm letting you be comfortable with the idea that the negative can float wherever I want it to go, as long as it exists somewhere in the fraction. I'll happily keep it on bottom for now, but don't be surprised if I ever move a negative up top, because it's not a negative, it's a negative 1. And dividing by negative 1 is the same as multiplying by negative 1. Spending a lot of time on negatives because people get uncomfortable with them. Perception is key, and knowing where to place something, or where you can place something, is all too important. Hey, I'm going to go ahead and swap the top and bottom here, and I get 2x times x plus 3 over x minus 12 times x plus 3. Now, this went from division to product. That's why these flipped. I didn't just flip them. Now that we're dividing numerator by denominator, let's go ahead and cancel things. X minus 12 over x minus 12. Excuse me, that's not an x minus 12. Yes, x minus 12 and x minus 12 go bye-bye. X minus 2 and x minus 2 go bye-bye. And x plus 3 and x plus 3 go bye-bye. I'm left with, now, what am I left with? I'm left with 2x divided by negative 1. So you can kind of see what I was saying about that negative there. Is that any different from 2x times negative 1? No. That negative 1 can happily float numerator, denominator, set of fraction, what have you. This is negative 2x. That's the final result of that one, as that's simplified. Of course, this is not without its restrictions here. What we're stating, once again, when we're simplifying, is they're telling us, or we're telling them, that this expression and this expression are the exact same. If I wanted to graph this, you know what I'm graphing? Just a line with a slope of negative 2. That's it. There is exception to this, though, because there are holes in the line. No pun intended, guys. There are actual holes in the line. There are jumps in the continuity. And they are for certain values of x that cannot exist here, which is, of course, x could not equal. You know, we're looking at that 2. X couldn't equal 2. Positive 12. Negative 3. And you might think that's it, because you look at these denominators and you're like, all right, well, that's all that was in the denominator. Wait, there's more. You have to remember, before we flipped this thing over, before this thing flipped over, these were in the denominator. Now, we already took care of -3, right? And yeah, we did. We already took care of -3. We didn't take care of this one. We didn't take care of this x. There was a time where if I substituted 0 in, that we would have been dividing by 0, just by plugging in 0 there. X also can't equal 0. For that very reason right there. Doesn't matter that it flipped later. It was in a denominator once upon a time. And that's another issue. That's another reason why before flipping this thing, we get some of the factorization out. Keep that in mind. Don't lose it. All right, there's that one. Let's keep going forward and let's look at 2 graphs. After this, we're going to do some addition, subtraction stuff. These might feel a little out of order regarding what you're doing here. We did addition, subtraction before the graphs, but I'm going to go in order of the way that I presented it for my students here, or the way that they can really look forward to possibly testing on it. All right, let's identify holes, vertical and horizontal asymptotes of each graph here and sketch the graph. Now, there's more than one way to do these kinds of graphs, and I'm going to go ahead and admit that the way that I'm graphing with you guys is out of a certain particularity. I'm really having you practice things involving stretch factor and making sense of it to be very common with everything you're doing for all transformations of all graph types. We've done quadratics and cubics. Later, after Thanksgiving break, you're going to see me do it on radicals such as square roots and cube roots. We're going to do them on exponential functions and logarithmic functions. So I'm doing them in such a way that we're making sense of how stretch factors apply to things of certain behaviors with that specific graphing form. When you graph rational functions of higher complexity, and trust me, these can get very complex as far as the things that can be involved. I don't mean they're hard. I guess they could be hard. But when it comes to certain complexities there, we're not going to worry as much about the stretch factor itself and just worry more about end behavior, intercepts, holes, asymptotes, and not all the very specific points that they hit. So what I'm doing with you is giving you a general behavior, a general understanding of why the rational functions behave the way they do when we divide by certain numbers. And keep in mind, it's a specificity that we would not do as we get more complex into it. So although we're doing it now, down the line, you're going to be paying more attention to the general understanding of everything as we just draw the curves but plot very specific critical features, like I said, such as intercepts, holes, asymptotes, the end behavior, the nitty-gritty in that way. I'm letting you know about it because next time I teach this in a pre-calc thing or something like that, there'll be a lot more. In fact, I have old videos that do it in such a way. That being said, there's more than one way that we can graph these, but if I'm going to graph the nitty-gritty in specific points, here's how I would do it. I would get it into graphing form. Graphing form looks like this, at least as far as a general version of it. It's a over x minus h plus k. A over x minus h, a being the stretch factor, h being a horizontal translation, k being a vertical translation. And also the asymptotes being a vertical line at x equals h and a horizontal asymptote at the line y equals k. So there's a vertical asymptote at x equals h, a horizontal asymptote at y equals k for this graphing form. Okay, so we're not in graphing form on numbers 5 and 6. We have to get into graphing form. How will we get into graphing form? Well, through some division tactics, of course, here. When I have 3x plus 9, I have a common factor of 3, and I'm left with x plus 3. And on bottom, x squared minus x minus 12 can factor into x minus 4 times x plus 3. Which leaves me with an x plus 3 over x plus 3 right here, which can, cancel. And we're left with 3 over x minus 4. So now I'm in graphing form. I have an a that is a value that is on top here. I have an x minus h, if you will. It's a 4 upside down, looks like an h. And my plus k, I guess, would be plus 0. I don't need to write that, but if that helps you recognize what it is we're doing, then hey, I'm going to go ahead and put the plus 0 there as well. So I do have a vertical asymptote at my x equals h, or x equals 4 here, and a horizontal asymptote at y equals 0. That's what that plus 0 is for. So I'm going to go ahead and give you some dotted lines here in blue on x equals 4. That's a vertical line. And y equals 0 right here. Now you might be wondering why we do a vertical line for a horizontal, Yeah, for a horizontal translation. Well, it's because we can imagine that the thing used to look like it was right here. Let me just do it on the vertical line. We can imagine that it used to be right here. And now we translated the vertical line 4 units horizontally. 1, 2, 3, 4. So everything is translated 4 units to the right. And the vertical line is just a representation of where we'd be dividing by 0. And we can't be dividing by 0. Speaking of which, the x plus 3's right here help us represent something else we can't have, which is the whole. The whole is where we are dividing 0 by 0, a value which we approach but don't actually hit. So the whole is at x equals negative 3. And when you refer to it as a point, not that it's an actual defined value, but it's where your curve would jump across, it would be at, plugging in negative 3 for x, not into here, because that gives you 0 over 0, but in the canceled version, that would give you f of negative 3 is 3 over negative 3 minus 4, which is negative 3/7. So the y value where you're going to see me draw a hole and have this appear is at negative 3 for x and negative 3/7 for y. About, I don't know, here-ish. Just a nice big old hole. And you're going to see how this comes into terms with the actual graph that I draw. All right, so there is the existence of the hole. Here are the asymptotes. How does the rest of the graph work? Well, it's all based off this 3 right here. As I displace myself from this new origin 1 unit over, I will divide 3 by 1, because that's 1 unit over, and I get 3. So I'm going to go 3 up and plot that point. Let's continue that. Let's divide 3 by 2, and we get 1.5. And let's divide 3 by 3, and we get 1. 3 by 4 is 3/4. I could keep going like that. I'll just get a little point right there. But at some point, you're like, not really worth graphing them. You'll like to see me do integers. I'm fine with halves like this, like 1.5 divided by 2. And I'm fine with getting a 1/2 out of what it is that we're going to do. Like 3 divided by 6, for example, would give me 1/2. Or 3 divided by 1/2 would get me 6, because dividing by 1/2 is multiplying by 2. 3 divided by 1/2 is 6. Let's go ahead and double that. If you haven't seen my graphing video, I think it's worth checking out when it comes to these specific points. But again, when we're off graphing form stuff in any future, whether it's future videos for this year or things that I can do of more complex variety, you won't see me find these specific points. What I want you to notice is the idea of convergence toward these asymptotes. As I keep dividing, I keep getting closer and closer to the number. As I divide by something closer and closer to the number, I keep getting taller, and things of that sort. I really want you to know where the values come from. I think that existence is important. Maybe someday it's not. I talk a lot. All right, let's divide 3 by negative 1, and it will get negative 3. So anytime, you're not going to hear me say negatives too much. I'm just going to say 3 down. 3 divided by 2 is 1.5 downward. 3 divided by 3 is 1 downward. So 3 divided by 4, 3 divided by 5, 3 divided by 6 is 1/2. So 1/2 down there. And then you get that 3 divided by 7. That's where you get that 3/7 down. Negative 3/7. That's where it comes from. You can see it just kind of keeps going. I could do, let's do 3 divided by 12. I can fit that. It's, I think, all the way over here. And that's negative 1/4. I want to fit that one because I can. 3 divided by 1/2 is 6 as we double the height and go there. Now, my students will, of course, ask how many points should they be plotting and doing. Plot every point that you want to. Definitely give me the whole. Definitely give me the integers. And really try and give me the half-C's. Give me the idea that you understand the convergence notion, that it's going to get closer to the asymptotes without actually touching. All right, so that is number 5 as a full graph. Holes. Identify whole, vertical asymptotes, horizontal asymptotes if they exist. I could talk about intercepts and things like that. I didn't really bring this up here. This was what, 3 divided by 4. So that's a y-intercept of negative 3/4. I'm just going to bring it up as far as the graph goes. There are different ways of coming up with these, of course. The y-intercept is substitute 0 for x. You get negative 3/4, right? So there are other ways you can do that, and that's obviously what you'll be doing in the future. There's no x-intercept because of the horizontal asymptote at y equals 0. Okay. Let's go ahead now and try and graph this one. F of x equals negative 2x minus 8 over x plus 1. Now, if you look, once again, this is not in graphing form. We don't have just a single value up top. And you can attempt to find the single value up top just like we did last time. We can attempt to factor, and we get negative 2 times x plus 4. Again, factor out the negative, divided by x plus 1. Now, nothing canceled. So, and I'm not going to say this isn't beneficial for you, but as far as getting in factored form, this didn't get us to where we needed. So what I'm going to go ahead and do instead is I'm going to do long division. I'm going to get this in graphing form, and we can, get those asymptotes and stuff the way that we've been kind of practicing and preaching here. And again, in the future, you'll probably see this in a different light. But for now, get some long division stuff, practice remainder. No problem with that. I'm going to go ahead and use long division, not synthetic. It's, hopefully you're okay with that. You got to know how to use long division because you can't always use synthetic division. X goes into negative 2x, negative 2 times. X times negative 2 is negative 2x. 1 times negative 2 is negative 2. Let's subtract the results there. Negative 2x minus negative 2x is 0. Negative 8 minus negative 2 is negative 8 plus 2, which is negative 6. That leaves us with a quotient of negative 2 and a remainder of negative 6. So another rewrite of this equation could be f of x equals negative 2 minus 6 over x plus 1. Negative 6 could not go into x plus 1 any certain amount of times, so it's still over that whole. And yes, this is graphing form, maybe not written the same order as this, so let's write it the same order as that. F of x equals negative 6 over x plus 1 minus 2. So here's our a, negative 6, over x minus h plus k. I know that's a plus, that's a minus. That's going to be the whole goal of identifying what those are. The vertical asymptote will be at x equals h. The h in this case is a negative 1. Remember flipping the sign because it's x minus h. The horizontal asymptote is at y equals k, and the k in this case being a plus negative 2. It's a negative 2 right there. So we're going to draw the vertical and horizontal asymptotes there at x equals negative 1 and y equals negative 2. X equals negative 1. That looks a little off there. Y equals negative 2. You got to draw actual dotted lines. I get a tool. And listen, there's no hole. There was never a time that we divided 0 by itself. There's nothing that canceled here, so no holes on this graph. But we do have to deal with the stretch factor of the negative 6. As negative 6 goes, we're going to go downward as we go to the right. Divide negative 6 by 1, we get negative 6. So 1, 2, 3, 4, 5, 6 is a point. Dividing 6 by 2, we get 3 downward. This is the negative 6. 6 divided by 3 is 2. See, dividing 6 by 4 might not be as fun for us. 6 divided by 5, no. But 6 divided by 6 is good. We get 1 from that one. And I'd love to get you something like 6 divided by 12. That's a little too far off the graph, though, unfortunately. I can do 6 divided by 8. How about that? That's 3/4. Let's get that. As we approach closer and closer, we can draw a nice, pretty graph right here as far as approaching goes. Yep, we're getting as particular as we can. And you know what? We also hit the y-intercept right there. This is the y-intercept of y equals negative 8. Not that I'm asking you to label those things. I'm just showing you as far as, at some point you'll have to. All right, so there's the y-intercept. Fun. We're going to also possibly land on an x-intercept, or we will. I don't know if it's a fraction or an integer. So let's see. Negative 6 divided by negative 1 is positive 6. That's why this goes upward. 6 divided by 2, 6 divided by 3. There's the x-intercept. Divided by 4, 5, 6. And those look like pretty good points there. 6 divided by 1/2 would be doubling that 6 and get like 12. 12, it's way up there. Kind of really hard to hit, but I'm going to put that as a top point as we get closer. Not the best looking curve there, but, doing what I can. Excuse me. And there's an x-intercept of negative 4. The x-intercept is negative 4, 0. Last time we didn't have an x-intercept. X-intercept means we set y equal to 0, either in this equation or this equation there, and we can actually find it pretty easily with that negative 4. Actually, if this was factored form, you would have seen where that negative 4 would have definitely come from right there. All right, and there's the graph of that one. So again, working very slowly and diligently with you guys through that. 34 minutes in. All right, that's 6 problems down. I got 6 more to go. Give me 1 sec, like 1 second. Okay, and I am back. Okay, so let's continue forward. And what we're going to do from here on out is addition and subtraction. A lot of dealing with getting a common denominator and such. Now, we just came off multiplication and division. We just came off graphing, but we came off the, as far as simplifying goes, multiplication and division. And, we were so gung-ho on finding factor. Well, we're going to still be doing factoring, but not on top, at least not yet. addition and subtraction are two separate fractions right now. We can't assume that they're being appeared as a single fraction just yet. Multiplication, you can. Division, you got to flip it, and then you can. But in addition and subtraction, we first need a common denominator. And after that, those terms, if they're factored, can't combine. The only way that we can combine the way that we want to is through keeping them expanded and separate, combining like terms. I'm not going to touch the top when it comes to factoring, even if it's factorable. I believe this is not factorable, but this one actually is right here. Don't factor it. We're going to leave them unfactored. We'll work on factoring the bottom. And when we simplify the top, when we write it as one fraction and all like terms are combined, if there's anything to factor then, we will happily do so in hopes that there's something that, or in anticipation for, there's something that can maybe cancel with the bottom. And, simplify this in a funner, more fun looking way. I'm not really sure what the word is when it comes to that. All right, so here we go. I will still look at the bottom. Now, here's a heads up, guys. We already have a common denominator. That's great. We want that common denominator here. Everything here is dividing by x squared plus 7x plus 12. Now, x squared plus 7x plus 12 is factorable. That factors into x plus 3 times x plus 4. But it's a common denominator already. That means I can combine the top things through subtraction. I have x squared minus 2x plus 3 that I can subtract with this whole quantity. Now keep in mind, if I subtract the fraction, it is subtracting the quantity in terms of everything being subtracted. Subtract x squared, subtract negative 4x, which is adding 4x, and subtract negative 5, which is adding 5. So I have a common denominator. I'm going to work on cleaning up this top in such a way x squared minus x squared is 0. I got a negative 2x plus 4x, which is a 2x, and a 3 plus 5, which is an 8. And this is still divided, of course, by x plus 3 times x plus 4. Now, we could be done, potentially, but there's a common factor up here of 2, which is something that I'd like to explore. When I factor that 2 out, I'm going to get x plus 4 inside. And check this out. I got x plus 4 on top. I got x plus 4 on bottom. I have cancel zone right there, x plus 4 over x plus 4. And so I'm now therefore left with just 2 over x plus 3. And that is the final simplification of this whole thing that turned into 2 over x plus 3. We're going to still do restricted values as we did before, things that x cannot equal. We look at any time that we could have been dividing by 0. Of course, negative 3 would get us to divide by 0. And as we talked about wholes and things like that, negative 4 would have presented a whole in such a graph here. X still can't equal negative 4, even if it canceled. And that is number 7. Okay, so that was an example of a subtraction problem right there. And this one appears as an addition problem to start with. I promise you it won't stay that way, as I got to do this problem earlier with some students. Number 8. We have x squared plus 3x minus 53. Again, don't attempt to factor, even though it's not factorable, and don't attempt to factor here. We're going to work on combining these top two things, provided that we get a common denominator. Now, this one's quite interesting because we have x minus 7 and 7 minus x. What you could do, and I would never actually have you do, what you could do is say, as far as common denominator goes, you want to multiply by the missing factors in the other fraction. So you can say, hey, see how this is a 7 minus x? It's missing an x minus 7. Let's multiply top and bottom by x minus 7, and let's multiply top and bottom here by 7 minus x. I wouldn't do that. You're going above and beyond something that's going to make this problem be a lot. It's going to be a lot for you. If you notice, guys, this x minus 7 and 7 minus x really are in that other problem that was like the x minus 2 and 2 minus x thing. 7 minus x really is just the opposite of x minus 7 in such a way that if I went ahead and rewrote this as negative x plus 7, which is the exact same thing. I changed nothing but the order. The x is still negative, 7 is still positive. We can factor a negative out of here, and we're going to be left with, excuse me, I just did that wrong. You factor negative out here, and you'll be left with x minus 7 like that. So there's an equivalent of this thing that can be written as, let me do that again, like this. This is the equivalent of the opposite of x minus 7, which now gets me essentially a common denominator, right? I mean, this is missing, this one's missing a negative 1. I could multiply this by negative 1 over, negative 1 over negative 1. But what if you don't want to do that either? Okay, this part's completely up to you. If you want to multiply by negative 1 over negative 1, nothing's lost. That's pretty good. Just distribute the negative 1 into these three terms here, and you're taken care of. But I want to still give you focus of the idea of what this negative is really doing in this fraction. And furthermore, the fact that we don't want negatives in our denominator, as far as leading terms, as far as factors go. Get this negative out of here. Put it on top. Make this plus a minus, right? There are a lot of options that we have here to do, and one of them is just, take this thing, get rid of that negative. We are adding a negative here. Whether you put it in denominator, numerator, that negative applies to the fraction as a whole. And this is things that these are the things people have trouble with. That's why I'm giving you this notion and this idea that this is how you should best approach this. Keep this x minus 7 as an x minus 7. Keep this x minus 7 as an x minus 7. Give yourself that common denominator here while you subtract this thing here. Get rid of that. And you really have to follow with me in this interactive state. That negative is now taken to that plus. I am now subtracting. This was subtraction. This is subtraction. So I'm going to subtract the quantity right here. Subtract all three terms. And I have x squared plus 3x minus 53 minus x squared plus 5x as we distribute the negative and minus 3. A lot of explanation for something that I hope you understood, right? I'm spending time to make sure you get some form of understanding. X squared minus x squared is 0. 3x plus 5x is 8x. That's a bad 8x. And negative 53 minus 3 is negative 56. And this is all divided by x minus 7. And again, would, should be done unless we can actually factor. Like this 8 appears a common factor. You factor the 8 out, you're left with x minus 7. This is divided by x minus 7. And x minus 7 over x minus 7 is a common factor. That becomes 1. And you are left with just 8. Who knew that this whole thing just is an 8? I did. I know. At least I got to it there. All right, restrictions. Well, in this case here, I didn't really do anything as far... Remember, this was 7 minus x before. X couldn't be 7 before. X still can't be 7 now. Factoring out the negative changed nothing about what x couldn't have been here. X can't be 7 in the scenario that... When could you plug something in for x anyway? I'll tell you what. It's still something. If you graph this, it's a horizontal line. You still jump it at 7. Okay, there's still an issue. I know there's nothing you could plug in here, but you could plug in a 7 there. So there is an issue, yes. So there's the restriction. X cannot equal 7. All right, let's keep moving forward. I have numbers 9 and 10, where once again, no common denominators, and let's aim toward our common denominators that we so yearn for. Number 9. We look at factoring the bottom here. I have 5 over common factor of x, and we're left with x minus 5, minus, a lot of minuses here, x over a common factor of 5, and we're left with x minus 5. So as we work for common denominator stuff, guys, we are trying to see, what's missing in the other fraction. They both share an x minus 5. This has a 5 where this does not. So let's multiply top and bottom there by 5. And this has an x where this does not, does on top. But, I guess this had a 5 on top. But let's multiply this by x over x. And what we're going to be left with here in this case, 5 is going to multiply with 5 to get 25. X multiplies with x to get x squared, minus x squared. And on bottom, we have the 5x times x minus 5 as a common denominator. Let's leave it factored, of course. Now, could, should be done unless there's something we can factor on top, and we totally can. This is a difference of 2 squares. It looks like it's a reverse order version, and that's something I think I want to take care of. See, this would factor into 5 plus x times 5 minus x, but you can tell it's also one of those things where, this wasn't in standard form. I have an x minus 5, and here I have a 5 minus x. It would be really nice if this was a version that was x minus 5. And, there's no dancing around the fact, guys, that we should put everything in standard form when we can. Like this x squared, 25 minus x squared is also the opposite of x. It's negative x squared plus 25, right? I didn't change anything. I just reordered the terms right there. But really what I'm looking to do is factoring out the leading negative. So if you factor out a leading negative here, you're going to be left with x squared minus 25, which is good, serious business, because now this difference of 2 squares will get us an x minus 5 factorization. this turns into x plus 5 times x minus 5, the x minus 5 that I was looking for to get that cancellation. This is one where you got to be a little creative. Well, I mean, part creative, but part understanding. Factoring out negatives, writing things in standard form. There's a reason these rules exist. They help us find things that we're looking for in such a way that'll be beneficial to us solving, simplifying and solving, right? So we're left with ultimately that negative, and I'll leave the negative factored out, but the x plus, you know what? I'm going to write the negative in front of the fraction, having you be wise in understanding that the negative applies to the entire fraction just as much as it would apply to -1 multiplied in the numerator or -1 in the denominator, which we do not want negatives in denominators. But here's how you would probably see an answer in a key. The -1 just in front of it multiplied by that whole quantity. All right, so as far as restrictions go, guys, x cannot equal 0, as, 5x couldn't equal 0, x couldn't equal 0, and x can't equal 5, and it looks like that was the only other issue there, 0 and 5 for restrictions. So there's the simplification of that. We are squared away. I got 3 more problems for us to do. We should be finishing by the hour mark. Let's go. Number 10. Dark green. I have 3 terms, 3 fractions here, and it looks like it's really worth kind of getting this one. This is x minus 1. This is a difference of 2 squares that we can factor here. Let's jump into that one. 7 over x minus 1 plus 10x over x plus 1 times x minus 1 minus 5 over x plus 1. All right. This has the x plus 1 and x minus 1 that these other things have. This guy right here seems to be missing the x plus 1. So let's go ahead and multiply that by x plus 1 over x plus 1. This seems to be missing the x minus 1. So let's multiply that by x minus 1 over x minus 1. And now we're going to have a common denominator. And in doing so, let's work on that top by distributing the 7 into these 2 terms. And distributing the -5. Remember, this is a -5. This is a -5 right here. And let's distribute it into those 2 terms right there. So 7x plus 7 is what we get from that guy. We're adding 10x here. And now this is -5 times x and -5 times -1. This is all dividing by the common denominator of x plus 1 times x minus 1. Now we're going to work on the combining like terms, doing things like that. 7x plus 10x minus 5x gives us 12x. 7 plus 5 is 12. This is dividing by x plus 1 times x minus 1. And all these problems so far with addition and subtraction have come with the reward of being able to factor something on top, being able to reduce it in such a way that you can cancel something on bottom. Not all problems are going to gift you this way. They're actually hard to come up with sometimes because they have to come out cleanly. But here is one that very much rewards you. And I like to reward my students on test day with those. We'll see how often they show up. But this becomes 12 over x minus 1 with the restrictions that x couldn't equal +1 or -1, of course, with the cancellation there. Let me put plus or minus 1. I like putting those when I can. All right, so x couldn't equal positive or -1. I got 2 more problems to do with you guys in there in terms of solving. Let's get right to them. It has the same thing to do with common denominators that it did before. I'll be honest, I don't know why I put number 11 first here. Number 12 is actually an easier problem to do. If you want, I could do number 12 first, but I'm not going to. Because you can't respond to me, and because I don't know what order some people might say, why'd you do number 12 first? When they're not listening and just writing things down. All right, number 11 here. We're trying to find common denominators, so let me kind of just rewrite these again. Because I'm going to factor anything I can, such as that bottom right there. So 2x over x minus 3 plus 6 over... All right, let's factor this guy right here. My hope is this is x minus 4 times x minus 3. And you know what? It is. -4 times -3 is positive 12. -4 plus -3 is -7. This is x minus 4 times x minus 3. Yeah, factor the bottom, guys. Look for what's missing on in the other fractions. Oh, we're actually missing an x minus 4 here. X minus 4 over x minus 4. And here, this one's missing an x minus 3 on bottom over x minus 3. All right, common denominator. Now, unlike the expressions, and listen, I I'm at pause for mentioning this because I mentioned it in class, I warn it in class, but some students still have trouble. And I'm not talking about just this year. Every year I do it, and I say this year will be different. This is an equation. This is an equation. In an equation, you can do anything to one side as long as you do it to the other side as far as manipulation goes, and as long as the math is accepting on it, such as we can't divide by 0. But I can multiply both sides of this equation by anything that I want to. If it allows me to clear a fraction, I will happily do so. Notice that we have a common denominator here, which means all of these are dividing by the same thing. Well, if I multiply both sides by the same thing, what happens is the fraction goes away. So I'm going to get a rewrite of this equation without the denominator, understanding that what I just did was I just multiplied both sides by x minus 4 times x minus 3 in a big, bad way. Right here and right here, x minus 4 times x minus 3. And now the bottom's just gone. It cancels out with what's up on top there. I can do that in an equation. This is an equation. I just did it. I know it's really messy looking now. I'd prefer not to get that mess. I cannot do this in an expression. Did you see me in any of the last 4 problems or the multiplication division problems? Did you see me get rid of the fraction? Besides, this part here. Did you see me get rid of it and say, oh, you know what? I'm just going to get rid by common denominator by. No, you can't do that. I can't multiply. I have to keep this equivalent here. Equations, I have to just keep balanced. I have to make sure the left and right side stay equal. In the expressions, I have to make sure that it stays true to the original expression that it was. Here, I can change whatever the heck I want. I can add 20 to both sides. It's not going to help me, but I could add 20 to both sides if I wanted to. Keep that in mind, guys. Once you achieve a common denominator here, you can ignore the common denominator because we can eliminate it by multiplying both sides by top and bottom by the same thing. Multiply both sides by the same thing, where it cancels top with bottom. I keep mentioning that because I do not want you to just get rid of fractions here. And I want you to understand the ease that we're going to use in getting rid of the fraction here. I hope that makes sense. Okay. I'm going to distribute the 3x into the x and the negative 3, and I'm going to get 3x squared minus 9x. Now I'm going to distribute the 2x into the x and the negative 4, and I'm going to get 2x squared minus 8x. And here I have a plus 6 as it multiplies with nothing. No denominator. I'm now attempting to solve for x in numerator. This looks like I have some quadratic stuff where I won't get rid of the quadratic. I got to subtract both sides by 2x here to get a positive x squared. Negative 9x, if I add 8x to both sides here, I get minus x. And I subtract the 6 over, I get negative 6, and that equals 0. I'm setting the quadratic equal to 0. If this is factorable, which it is, I can then solve this guy by factoring. Finding 2 numbers that multiply to make negative 6 and add to make negative 1. That's a negative 3 and positive 2. X minus 3 times x plus 2. And in solving this using the zero product property, if a times b equals 0, either a equals 0, so x equals 3, or b equals 0. So x equals negative 2, and those would be our 2 solutions. But you want to make sure that neither of these are what are called extraneous, meaning the same thing as before. What would have been restrictions here? X couldn't equal 4, or x couldn't equal 3. Well, guess what? We just got the solution x equals 3. That's a problem. Now, I don't need to write restrictions here. I need to make sure that my solutions aren't restrictions, and one of them very much is. 3 cannot be allowed as an answer. 4 couldn't be either, but you know what? Nothing else could besides negative 2. Negative 2 is the only acceptable answer. 3 is what's called extraneous. It was introduced once I multiplied. See, it was introduced the moment I multiplied both sides by x minus 4 times x minus 3. I created a quadratic where a quadratic didn't otherwise exist. So I created a new solution that never should have been there, or that doesn't know that we were possibly dividing by 0 if we plugged in 3. So that's extraneous. The only solution is x equals negative 2. All right, this last problem is no harder. You're going to have a quadratic. It's just that there's less to do in terms of the common denominator front. I guess that's the reason why it's easier than the other one. But it has all the quadratic stuff that we have from this last problem. Now, x is x over 1. I want to just let you know that, the denominator is 1 there when it comes to trying to achieve a common denominator. So what I'm going to do is multiply top and bottom this guy by x minus 3, as it's the only one that doesn't seem to share the same denominator as the others. So, okay, guys, I've achieved a common denominator already. excuse me. And just like last time here, now that I have a common denominator, you can essentially get rid of the denominator because it's an equation. Multiplying both sides by x minus 3, they're gone. Now that they're gone, I'm going to distribute x into the x minus 3 right here, and I'd be left with x squared minus 3x. Now I have this plus 6, and this equals 2x. Again, denominator be gone. Let's subtract 2x from both sides, and I get x squared minus 5x plus 6 equals 0. All right, I need to find two numbers that multiply to make positive 6 and add to make negative 5. That's a negative 3 and a negative 2. Very close to the last one as far as the appearance of factorization. This was x minus 3 times x plus 2. This is x minus 3 times x minus 2. All right, so when solving this one using zero product property, either x equals 3 or x equals 2. It's again kind of reversing the signs there. We've done a lot of those before. Now, once again, we got to check for restrictions. It looks like there is, guys, once again, an issue regarding x equaling 3. If x equaled 3, I would be dividing by 0 here. So I really seem to have a problem with the number 3. X equaled 3 right here? Nope. X equaled 3 right here? Nope. Once again, not extraneous, but extraneous. That is an extraneous solution. X equals 2 is just fine. X equals negative 2 here was just fine. Those are our solutions. And that is it, guys. That is the end of the review for this one here. Thank you so much for watching. This is Mr. Robinson, and make sure you check the description section down below for any timestamps of any things that I may have missed, assuming I put it up. Sometimes I forget to put them up in time. But that ought to be it, guys. Thank you so much for watching. Ask me any questions in the comments that you can, and I will see you in the next one. Take care.